Okay, folks, so we're going to talk now about sequences. And in class, we talked about this a little bit. One example was repeating over and over again 8675309, which is a nice kind of sequence if you like 80s pop music. But in general, a sequence is just an ordered list of numbers that goes from, so you can say that there's a first element, second element, third element, so on in the list. And it might be a finite list of numbers, or it might be an infinite list of numbers. Closely related to how we're going to use sequences is the idea of a limit, which is a sequence that goes toward a particular direction. That's going to be really important as we think about series, which is like a sequence, except you construct it by adding a little bit more each time as you head towards maybe an infinitely long sum of different terms. So let's first talk a little bit about limits, and then we'll talk about the kinds of sequences, and then we'll start to get a handle on sequences that definitely have a limit that's easy to think about. Okay, so if we have a function, f of x, and x is the independent coordinate, then a is, say, a value that we're interested in the function of f of x near a. Then, suppose here's our function. We might say, I could call this the limit of the function f of x at a if it's close as x approaches a, if it's close to the value at that point. And we can be a little bit more precise by saying, suppose I take a little range around that limit, so plus or minus epsilon, where epsilon is any number you like, any threshold. And if I can give you a delta, which is a distance away from a, plus or minus delta away from a, and I can say that if I'm in this range of the deltas, the function always stays within an epsilon distance of this value, then that value can be taken as a limit. What we really mean by the limit, though, is don't just do that once for one particular epsilon or one particular delta, but you tell me what your tolerance is epsilon, and I can say it's the limit. If for any epsilon you choose, I can give you a delta that's small enough that I can then say the limit of f of x as x goes to a is this value, which we haven't given a term, but let's call it L. So here's L, L plus epsilon, L minus epsilon. This is what we mean by the limit. If for any epsilon you give me, I can give you a delta that gets you so that you're always in that box. Okay? So the function stays in that box. But what if we're not talking about the limit as we approach a particular point, but what about the limit as x goes to infinity? Then we might have a function, say it does whatever it does. Again, we make a little box and we say, here's our limit. Limit plus epsilon, limit minus epsilon. And what you're claiming is that for some n, and all the n's that are bigger than that, the function stays within the box defined by that range around L. So in that case, we would say the limit as x goes to infinity of f of x is equal to L. Okay, great. So that's what we mean by limits in terms of functions. And we'll come back to both of these again as we think about calculus. But for now, this one's a more interesting one because we can take advantage of this by imagining a sequence as being just a list of values following along this function. And then we can think about the limit of a sequence by being the list member on that list in the sequence that always stays within a particular distance of the ultimate limit. Okay, so what are some sequences? So we said 8, 6, 7, 5, 3, 9, and repeating. That's not a very interesting one. Well, not mathematically interesting anyway. Another one is just the counting numbers. 1, 2, 3, 4, 5, 6. This is an example of an arithmetic sequence because the difference between them is constant. It's just 1 in each case. Another arithmetic sequence could be 2, 4, 6, 8, 10, or whatever ratio or fraction you want to add to each one. 1/2, 1, 3/2, 2, etc. Arithmetic sequences don't tend to go to a limit because you're just always adding on a little bit more each time, and that amount isn't decreasing. If the amount were decreasing, we might think that this might or might not reach a limit. We'll get to that when we get to series in the next short video. But what about a geometric sequence? A sequence like 1, 2, 4, 8, 16, 32. Okay, that's the one where I'm multiplying by 2 each time. That clearly doesn't have a limit as well. But what if I divide by 2 or multiply by 1/2 every time? 1, 1/2, 1/4, 1/8, 1/16. That clearly does eventually get to be 0 as its limit, as n goes to infinity. And how can you say, well, I can say, I demand that you make it closer to 0 than 1/64. So we haven't gotten there by 1, 2, 3, 4, 5, 6, 7 would be 1/64. And from 7 on, it's always smaller than 1/64. And so that's what we mean by the limit being bound. Okay? By this little epsilon plus or minus. One other quick note that I forgot to mention, we didn't have to pick a positive ratio between the numbers. We could have taken negative 1/2, and then it would have gone 1, negative 1/2, positive 1/4, negative 1/8, positive 1/16, and so on. That still converges to 0 in the end. When we have an alternating series, that is when we're adding on a little bit that's changing its sign, we have to be more careful. But for sequences, it's not too much trouble to think about it that way.